Welcome. In this video, we're going to look at the topic of representing data using bases for subspaces. So our objectives are to first of all introduce the idea of bases as building blocks for subspaces. We'll then look at a couple examples and define what we mean by orthonormal bases. Now, we've mentioned in a previous video that subspaces are extremely useful in machine learning. And we define subspace as the span of a set of vectors. So let's suppose I have a set of vectors v sub I. Then I can define a subspace S as all vectors x which can be expressed as a weighted sum of the v sub I, where the weights w are real numbers. And this is what we mean by the span of v sub I. Now the v's help us define what we mean by the subspace. If the v's are arbitrary vectors, it can be very difficult when they are linear dependent, because then it complicates computation and interpretation. So often we prefer to have a set of v's that are linearly independent. And in some cases, we want the v sub i's to be a set of orthonormal vectors. Orthonormal vectors are the very easiest to compute with. Now, in the second and third case, where we have a set of linearly independent vectors, we call these v sub i's that describe this subspace, we call that a basis for the subspace. There's a unique relationship between a vector in the subspace and these coefficients, the w's, that express that vector as a function of the v sub i's, or the bases. And the relationship is always unique for these second and third cases when we have linearly independent vectors. Now briefly, orthonormal is a word that means the v sub I are orthogonal to each other, and they're also unit length. Their inner product with itself is 1, that's unit length, and the inner product between any two different v sub i's, v sub I and v sub j, is 0. Remember that the inner product between two vectors can be expressed as the magnitude of one times the magnitude of the other times the cosine of the angle between them. So if the cosine is pi over 2 radians, or 90 degrees, then the inner product is 0, and that's what we mean by these vectors being orthogonal to one another. So suppose I have two vectors, v1, which is in orange 1, 1, 0, and v2, which is 0, 1, 0. These are vectors in 3 space, which we'll refer to as x, y, and z coordinates. We're going to consider these to be a set of bases. We can graph them, as I've done here with the orange and the green vector. You can see that the span of these vectors is the xy plane. I can take weighted combinations of these two vectors and get any point in the xy plane. So we would say that this is a two-dimensional basis for the xy plane. In other words, we have a two-dimensional subspace in three-dimensional space, and any point in that space can be expressed as v1 times w1 plus v2 times w2. Now these vectors are not orthonormal, because you can check that v1 transpose v1 is equal to 2, so v1 is not unit length. Furthermore, they are not orthogonal with one another, because v1 transpose v2 is also not 0. However, if I redefine v1 and v2 slightly, I can come up with an orthonormal set of bases. So let's define v1 to be 1 over the square root of 2, 1, 1, and 0. So I've just changed the length of the v1 in the previous example. And then we'll define v2 to be 1 over the square root of 2 times minus 1, 1, and 0. Now I've graphed these two vectors, and you can check and see that both of them have unit length. The inner product of the vector with itself is 1. And if I do the inner product of v1 and v2, I get exactly 0. So those are orthogonal to one another, as depicted in the picture. And these vectors also form an orthonormal basis for the xy plane. So there's two vectors here. They span a two-dimensional subspace, which in this case is the xy plane. Now in this third example, I've chosen v1 to be 1/2 times 1, 1, 1, 1. This is a 4-dimensional space now. v2 is 1/2 times 1 minus 1 minus 1, 1. And V3 is 1/2 times 1, 1, minus 1, minus 1. These vectors span a three-dimensional subspace of four-dimensional space. And they form a basis for that space, meaning that any vector in that span could be expressed as a weighted combination of V1, V2, and V3. You can check that these vectors are also orthonormal because the inner product of each vector with itself is equal to 1. V1 transpose V2 is 0. For the same reason, V1 transpose V3 is 0, and you can check that V2 transpose V3 is also 0. So in this case, all three vectors are orthogonal to one another. They also have unit norm, so we say that they are an orthonormal basis. Here I have a graph that represents the fractional value of a vehicle, for example, as a function of time since the vehicle was new. So we've got two different cases that are illustrated. In one case, the vehicle that is in red initially loses its value at a faster rate, but then the loss of value tends to taper off in the later years, whereas the vehicle in blue tends to hold its value initially, and then the value loss accelerates. So we decide we're going to model the fractional value, p, as a function of time as W1 times Ti W2 plus Ti squared W3. So we're going to describe this as a constant term plus a linear term plus a quadratic term. So I can take all 121 measurements from the 121 months that I have data on a particular vehicle and find a model for this vehicle that's quadratic by saying that price values are equal to this matrix times some coefficients. What's happening here is that we're representing the price vector, which is 121 dimensions, as a sum of a constant vector V1 plus a linear vector term V2 plus a quadratic vector term V3, where W1 is the basis coefficient associated with the constant basis V1, W2 is the coefficient associated with the linear basis term V2, and W3 is the coefficient associated with the quadratic term. So the data itself is 121 dimensional, but if I use this model, I'm compressing it down into three-dimensional space because these three parameters, W1, W2, and W3, describe the price data. So here I surveyed a whole bunch of vehicles and for illustration, and it turns out that we find three different possibilities in the set of data that we had. The quadratic coefficient, in other words W3, is being shown on the vertical axis, and the linear coefficient is being shown on the horizontal axis. So if we take the vehicles that end up in red here, what this represents is the linear coefficient is the most negative of the three cases. And so these vehicles have a fairly large negative linear slope. The quadratic coefficient is positive. This is going to lose value initially and then tend to hold its value later. So that's going to be somewhat similar to this red curve here, where we have an initial linear slope and then this positive quadratic term tends to level off the losses associated with the linear term. Now the cluster of data that's associated with vehicles represented in blue, those tend to have fairly small negative slope in the linear term. And so those tend to hold their value initially, but then they have a negative value in the quadratic coefficient, so they're going to tend to lose their value later. And that would be representative of this blue curve. Now for fun, we threw in a few vehicles that have fairly steep linear slope and also have this negative quadratic component. And so these are losing value rapidly all the time. So here we're working in a three-dimensional subspace, and we're only looking at two of those three dimensions in this particular plot, and they're fairly informative, and they tell us whether a vehicle loses value initially and then holds it later, loses and loses, or it holds its value initially and then loses it toward the end. For a second example, we're going to revisit the movie ratings problem, where we ask people to rate four movies: The Last Jedi, Star Trek, When Harry Met Sally, and Groundhog Day. Last Jedi and Star Trek, we're going to classify those as science fiction movies. When Harry Met Sally and Groundhog Day we'll call romantic comedies. And then When Harry Met Sally and The Last Jedi both have Carrie Fisher as a lead actress in them. So we want to explore people's preferences for these movies. We're going to hypothesize that there might be a difference between science fiction and romantic comedies. So we'll define one taste profile as having +1s in the sci-fi positions and -1s in the romantic comedy positions. And then we'll have another taste profile associated with Carrie Fisher. And so here we'll be using the ones to represent an affinity for Carrie Fisher movies, and the -1s to represent a distaste for Carrie Fisher movies. And we'll describe or approximate any individual's ratings as a weighted sum of these two taste profiles. Each of these ratings, we're going to approximate it as lying in a two-dimensional subspace, because we have these two basis vectors, T1 and T2. Now the data itself is four-dimensional because there's 4 movies, but we're only going to look at these two components. We'll take 100 people and look at their ratings. Now it's difficult to view data in 4 dimensions, and if we were to scale this problem up to something realistic where we have hundreds of movies, then it would be impossible to visualize. But we can visualize it in terms of a small number of taste profiles. So let's suppose that we take these 100 people and we plot their weights, W1 versus W2. So on the horizontal axis, we've got W1. On the right, we have a positive value for W1. That's a positive value on these first two terms of the taste profile, which means people are rating the sci-fi movies higher than the romantic comedy movie. Now on the other side, when the weight W1 is negative, people are giving a higher weight to romantic comedies than sci-fi. And if we're at either ends of the axis, these are people that have very strong preferences. For example, this person here is a very strong preference for sci-fi over romantic comedy. And on the other extreme, we have people that have a very strong preference for romantic comedy over science fiction. Now on the vertical axis, we're showing the preference for Carrie Fisher, which is in the upper part here, positive coefficients, versus the non-Carrie Fisher movies, which would be having negative coefficients. So if the data for our 100 people that we sample happen to look like this, you'd conclude, because the spread along the sci-fi romantic comedy axis, the spread there is much greater than the spread along the Carrie Fisher axis, you'd conclude that in general, population that you surveyed has much stronger preferences for sci-fi versus romantic comedies than they do for Carrie Fisher or non-Carrie Fisher movies. The other thing is that there's no obvious trends in this data other than the one we just mentioned. So it's not like there's a link that people who generally prefer sci-fi also generally prefer Carrie Fisher movies. If people like sci-fi, it doesn't really tell us much at all about whether or not they like Carrie Fisher movies. Or if they like romantic comedies, it doesn't tell us much either about whether they prefer Carrie Fisher or non-Carrie Fisher movies. Now on the other hand, suppose we were to survey our 100 viewers and we came up with the following sort of results. Well, in this case, because the data cluster is tilted along a diagonal, we conclude that there's a link between the preferences for sci-fi and romantic comedy with preferences for Carrie Fisher or non-Carrie Fisher movies. People that tend to like sci-fi movies also tend to like Carrie Fisher movies. And the opposite is true. People that tend to like romantic comedy movies tend to prefer movies without Carrie Fisher. By mapping this data into a lower dimension, we're able to draw some conclusions from the data that would be otherwise very difficult to draw. It also can help us with prediction and identifying patterns. So we've introduced the idea of bases as building blocks for subspaces, and those bases are a tractable way for us to define subspaces computationally when we work with them in machine learning problems. Now, we've only touched on this subject, and we're going to revisit this over and over again, and there are a number of issues at this point that remain open that we will look at as we go on further in this material. One issue is, how do you choose a good or a useful basis? And we may want to let the data define what the basis is rather than our prior expectations. What dimensions should we choose for the subspace? In other words, how many basis vectors should we use? And if I give you a set of bases and you have some data that you want to represent in terms of those bases, how do you find the basis coefficients? And then another topic is, suppose I have some set of linearly independent vectors, or maybe they're linearly dependent. Can I take those vectors and find an orthonormal basis?